Okay, hello. I'm going to try something new, which is to run through some of these Regents questions with you. I'm going to try to move kind of quickly here and solve them, give you some clues along the way on how to solve these. So this is on forces right here, and there are about 70 questions. We'll see how many we get through. Let's start with number one. Which cart has the greatest inertia? You see the word inertia? Just write mass. Therefore, 1, 2, 3, 4 kilograms. 4 kilograms. Mass is in kilograms. Which person has the greatest mass, right? 110 kilogram wrestler is the biggest of the bunch because mass is in kilograms. Boom, there we go. Compared to 8 kilograms of feathers, 6 kilograms of lead does it have less mass and less mass? Less mass and more mass? Well, definitely not that, right? So it's got to have 8 kilograms compared to 8 kilograms. 6 kilograms has to have less mass and less inertia. So let's go less mass and less mass, less inertia. Okay, what's an essential characteristic of an object in equilibrium? Equilibrium means the forces are balanced. If the forces are balanced, that means you have zero acceleration. You can be moving. If you're moving, it's just you're moving at a constant speed. In which situation is the net force equal to zero? That would be an equilibrium problem. So even though A is moving at a constant speed, because it's circular motion, the direction of the velocity vector is changing. And if the direction is changing, that means you're accelerating. So one of the tricky ones with constant speed, where it's not in equilibrium. Everything else, let's see, hit by a bat, speed's changing. Constant speed right here, net force is equal to zero in equilibrium. If you're moving at a constant speed and your direction of motion is not changing. The sum of all the forces acting on a moving object is zero. The object well, it's not going to slow down and stop. It's going to continue at the same speed, right there with a constant velocity. If it was stopped, it would stay stopped, but if it's in motion, it will continue moving at the same speed. A man standing on a scale in an elevator notices that the scale reads 30 newtons greater than his normal force weighs. What type of motion could the elevator be doing? So that means if his weight is down, the normal force is bigger, so he should have a net force up and an acceleration upwards. So he will be accelerating upwards. You don't know the direction of motion. He could be going upwards and speeding up, or he could be going downwards and slowing down. But either way, the acceleration is upwards. Which graph best represents the motion of an object that is not in equilibrium? Not in equilibrium means that the speed is changing. So a dt graph should be curved. That's not right. Speed versus time graph should be slanted. That should be the slope of that should be your acceleration. So that's going to be the correct answer. There we go. If you had a dt graph, this is dt moving at a constant speed. That is not the correct answer. It would be curved upwards or potentially curved downwards. Definitely curved in some way, depending on whether it was speeding up or slowing down. Go to the next page. 3 forces act on a box on an inclined surface: the normal, the weight, and the friction. The box at rest, the net force is equal to at rest, means you're balanced, so the net force has got to be 0. That also means that your component of the weight, this is your weight sine 30, weight sine theta, if that's your angle theta right there, is going to equal to the frictional force. The force up the incline has got to equal the force down the incline, and the force down the incline is weight sine 30. That is not on the reference table. Person is standing on a bathroom scale in an elevator car. The scale reads a value greater than the weight of the person at rest. Again, just like the last one, the scale tells you your normal force. You got more force up than down. Then you could be going upward at an increasing speed. If you were going downward, you would be going downward at a decreasing speed. That is not a choice, so that is a valid choice. Which two graphs represent the motion of an object on which the net force is 0? Net force is 0 means equilibrium, so equilibrium means constant speed. This could be constant speed, but that's definitely not. That speed is changing. Constant speed would be like a this or this, so it's got to be B or D. And if the net force is 0 and your speed is constant, that means the slope of dt, which is your speed, so the slope of this should equal that. That's going to be answer B. This would be accelerated motion, and the speed graph would be like this is an object not in equilibrium. That is a valid graph. A and D are not graphs that are valid for a particular motion. Second law, spring scale reads 20 newtons. It pulls a 50 kilogram mass across the table. What's the magnitude of the force exerted by the mass on the spring scale? I said second law. It sounds a little bit more like third law to me, because the spring scale reads 20 newtons. What is the more the force exerted on the mass by the spring scale? Should also be 20 newtons. Okay. Here we go. Net force of 25 newtons is applied to a 10 kilogram block. What's the acceleration? Acceleration is net over mass. Net force. If you know the net force, you know the mass, you can always find the acceleration. In this case, 25 newtons over 10 kilograms gets you a net force of D, 2.5 meters per second squared. Let's go to the next page. We're just blowing through these quickly. Two forces are applied to a 2 kilogram block on a frictionless table. This pretty much says exactly what's in the picture. The acceleration of the block is, well, we know the mass of the block, and we know what the individual forces are. We can find the net force. If there's 8 left and 3 right, your net force is 5. That's a 5 left. So your acceleration is net force, 5 newtons over 2 kilograms, gets you 2.5 to the left meters per second squared. B. 2 kilogram body traveling at a velocity of 40 meters per second east. A constant force of 10 newtons is applied for 5 seconds. The final speed of it is, well, it's initially at rest. There's a lot to unpack in this particular question, but we know that acceleration is net force over mass, which is going to be 10 newtons east over 2 kilograms, or 5 meters per second squared. Well, that means if time equals 0, its velocity is equal to 0. Time equals 1, it's now going at 5 meters per second. Time equals 2, it's going at 10 meters per second. Time equals 3, 15, etc., etc. So 4 or 5 seconds, the speed should be 25 meters per second, going east. Oh, wait. Mistake on my part because I misread the question. I wasn't reading carefully. Its initial velocity was 40 meters per second. Oopsies. So it's 40 meters per second east, and the force is east. So that means originally, if you do this, A is delta V over T, means your change in velocity is going to be 25. You can put these into the kinematics equations and work this out for yourself. V final minus V initial. So V final is going to be VF minus 40 over 5 seconds should equal 5. So 25 plus 40, meaning our change in speed is 25, but we started at a speed of 40. Should be answer C, 65 meters per second. Glad I caught that one. A constant unbalanced force is applied to an object for a period of time. Which graph best represents the acceleration of the object? Constant force. So if your force is constant, that means your acceleration is constant. Means your acceleration is not changing, and the only one that has an acceleration not changing would be answer D, number 16. 17, in the diagram below, blah, 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 two forces. I mean, honestly, look at the diagrams. That's more important than what it says sometimes. The magnitude of F1 is greater than F2. Well, clearly you're going to have a net force to the right and then an acceleration to the right. So which of these indicates that? It could be moving at a constant speed. Nope, not a constant speed. It's going to be accelerating to the right, which is the direction F1. Answer C. The forces and the acceleration. What's the inertial mass? Remember, we see inertia, we can replace it by mass. What's the mass of the object? Well, mass, if you look at the equation F equals ma, net force equals ma, mass is just net force over acceleration, which in this case is the slope of this. Net force is the y-axis, acceleration is the x-axis. So if you got 1.5, goes up 1.5 and over 3, delta y would be 1.5, delta x would be 3. 1.5 over 3 should be a ½ kilogram right there. Answer C. 1.5 over 3 is a half. Okay. Two graphs. Unbalanced force for block A, unbalanced force for block B. This is steeper. Remember, force versus acceleration. This is going to be mass. So compared to the mass of block A, the mass of block B has a bigger slope, should be a bigger mass. Oh, they're asking me whether it's twice as great or 4 times as great. So it's got to be one of those two. Let's see, this goes up 3 and over 3, so that's got a mass equal to 1. This one goes up 3 and over 1.5. So m is equal to 3 over 1.5, which is 2, so twice as big. Okay. 2 kilogram block moving across a frictionless surface by a 6 Newton horizontal force. What's the acceleration? Acceleration is just, in this case, net force over mass, or 6 newtons. Only force that they show, right? It has an up and a down, has a normal force and a weight, but they cancel each other out, meaning the applied force is the only one left. That's going to be your net force, 6 newtons over 2 kilograms, so 3 meters per second squared. A container of rocks with a mass of 65 kilograms is brought back from the moon. Oh, mass of 65 kilograms. That's important to note because the mass does not change. What's the weight of the container on the Earth's surface? We don't even care about this 1.62. You could use that to figure out the weight on the moon, but right now we're doing the weight on the Earth's surface. F sub g equals mg, which is 65 kilograms, times the acceleration here on Earth's surface, 9.8 meters per second squared. It's going to be close to 65 times 10, 650. So probably this has got to be the right answer. Okay. The acceleration due to gravity on the surface of a planet is 19.6 meters per second squared. If the object on the planet weighs 980 newtons, the mass of the object is, so weight F sub g equals mg. So 980 newtons equals mass times g, but let me just bring g over here. So 980 divided by 19.6 should be 980, 50 kilograms. Boom, right there. Doing a good job so far. 60 kilogram skydivers falling at a constant speed. Oh my gosh. So they're falling, but it's a constant speed that's balanced. That's probably because you have significant air resistance that is equal to the weight of the person falling. So that means, if that's your weight, that's your air resistance. And so the force of air resistance should be equal to the weight, and the weight is 60 kilograms times 9.8 meters per second squared. It's still pretty close. So it's around 600. It says it's approximately 600. So they're both 600. An apple weighing 1 Newton has a mass of approximately, well, we could do, again, F sub g. 1 Newton equals m times 9.8 meters per second squared. That's going to get you a mass of about, squiggly lines for about, 0.1 kilogram, or 10 to the negative 1th kilograms, should be answer A. An astronaut has a weight of 560 newtons on the planet Alpha. What's the acceleration due to gravity? G equals F sub g over m. So 560 newtons over the mass of 70 kilograms. 560 divided by 70, I should know this, should be 80. No, wait, 8. That's right. 8 meters per second squared. Not Earth. If it was Earth, it would be 9.8. Okay, the magnitude of the acceleration due to gravity on the surface of planet X is twice as great as the surface on planet B. What's the ratio of the mass? What is the ratio of the weight of mass X on the surface of planet A to the weight on the surface of planet B? So the mass is going to be the same, but F sub g equals mg. So if you have acceleration that's twice as big on planet A, as planet B, that means it's going to weigh twice as much on planet A than on planet B. So it says, what is the ratio of the weight on the surface of planet A to planet B? Well, it's going to weigh twice as more on A than it will on B. So the answer should be 2 to 1. That's answer B. 15 kilogram mass weighs 60 newtons on planet X. It's allowed to fall freely. After falling for 6 seconds, the acceleration of the mass is, well, the idea of free fall is that the acceleration is not going to change. It's always going to be g. G is the acceleration of a falling object. G is F sub g over m. So you should have 60 newtons. The weight divided by 15 kilograms gets you 4 meters per second squared. My pen's dying. I'm going to get a new pen. Okay. On to the next one. The graph representing gravitational force and mass. Well, this is slope is y over x. Y over x is force over mass. F sub g over m. F sub g over m is going to equal g, the acceleration due to gravity on this particular planet. Answer A. Switch to black ink this time. Okay. Gravitational force, by the way, is weight of the object. Keep in mind that those are the same thing. 50 kilogram block, a 5 kilogram block on a horizontal surface, it's at rest. So it's got a force down that is equal to its weight, mg. 5 kilograms times on the earth, 9.8 meters per second squared. So 49 newtons down. So it also has to have 49 newtons up. And it says, what is the force exerted on the block by the table? That is the upward force. So that is going to be 41 newtons. Answer A. Don't get confused. Some of them throw in kilograms. That is not a force. On to question 30. 2 carts are pushed apart by expanding springs. If the average force on this cart is 1 Newton, what's the average force on this cart? Well, Newton's third law, action-reaction, they should be the same force, also 1 Newton. A man is pushing a baby stroller. Compared to the magnitude of the force exerted on the stroller, the magnitude of the force exerted on the man is exactly the same. Newton's third law, action-reaction. They don't always have the same acceleration, but they do have the same force. High school physics student is sitting in a seat reading this question. The force with which the seat is pushing up on the student is closest to, it's got a lot of numbers, right? It's not going to be 0. We know that. Let's say your average high school student is about 60 kilograms. That's about 600 newtons. So if he weighs or she weighs 600 newtons, the force up from the table is also 600 newtons. If not, then the person would be falling down through the table or the chair. The magnitude of the gravitational force on the Earth on the moon is F. The magnitude of the force of the moon on the Earth is also F. Equal and opposite. Forces always come in pairs. They don't have the same acceleration. The moon's going to have a much bigger acceleration because it has a much smaller mass to it. The magnitude of the force on a baseball bat is 50 newtons. The force the ball exerts on the bat is 50 newtons. Third law. Okay. A ball having mass m is struck by a bat having mass 9m compared to the magnitude of the forces. Wow, there's a lot of similar stuff. Force is going to be the same. C. Mosquito flying compared to the force of the truck on the mosquito. The magnitude of the force of the mosquito on the truck is the same. Third law. Wow, it's all a lot of the same forces. Friction. Okay. A box is being pushed to the right across a crossing floor. The force of friction on the box is directed to the, well, if it's moving right, friction is going to be opposite, left. The force required to start an object sliding across a horizontal surface is larger than the force required to keep the object sliding at a constant speed. This is basically a way of saying static friction is bigger than kinetic friction. The magnitude of the forces are different in these because the force of kinetic friction is less than the force of static friction. Okay, when a 12 Newton horizontal force is applied to a box on a horizontal tabletop, they throw in all these extra words, horizontal, horizontal. It just means it's being pushed sideways. The box remains at rest. The force of static friction is, well, static friction means the forces need to be balanced. The object's not moving, so if you apply 12 newtons, there's got to be 12 newtons in the opposite direction. Sometimes they'll give you the mass or you can figure out the coefficient of friction and use the Fun equation. and you'll get a number bigger than 12, well, it's always going to still be equal and opposite to your applied force if it's not moving. It's got to be balanced. Going on to the next page. In the diagram below, the upward drag force opposes the parachute, equal and opposite, blah, 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 blah. The result of the force is shown. The parachute may be moving. Well, if these forces are equal and opposite, the person is clearly probably moving downward, but they're going to be moving downward at a constant speed. It's unlikely that they would be moving upward at a constant speed, but that's not even a choice. It is possible, I guess, you could have someone moving upward at a constant speed, totally. So, but they have decreasing or constant acceleration. Downward at a constant speed is answer B. We got a block sliding down an incline, which represents the frictional force acting on the block. The block is sliding down in direction D, so opposite that is direction B. A 50 Newton horizontal force is required to keep an object weighing 500 newtons moving at a constant velocity. Constant velocity is always important. Let's keep that. 2 meters per second across the horizontal surface. I'm guessing this 2 meters per second probably is unimportant right there. We don't even need to know that. You just need to know that you're applying 50 newtons of force to an object. The magnitude of the frictional force has got to be if you're applying 50 newtons, frictional force has got to be also 50 newtons to have balanced forces, because constant velocity tells you forces are balanced. Answer C, 50 newtons. A wooden block is at rest on a horizontal steel surface. Steel, that's something important to know. A wooden block and a steel surface, there's a good chance we need to look up the reference table. 10 newtons is applied parallel to the surface to set the block in motion. How much force is required to keep the block moving at a constant velocity? That tells us we're going to need kinetic friction. Now, they actually give us more. So they're telling us with the static friction equation, force of friction equals mu times the normal force, you need 10 newtons to set the block in motion. Static friction is always going to be less than that. So it should definitely be less than 10 newtons. You don't know what... Well, we could do some math to figure out wood on steel, for example. If we knew the coefficient, we could find the normal force. We don't even need to do that. We just know that it's less. Okay. Sand is placed on an icy road because it increases the coefficient of friction. You want more friction to be able to control your car. So, answer B. Does not increase the normal force. That would also increase frictional force, but that would basically be meaning that you're driving a heavier car, because normal force would be equal and opposite to weight. Okay, you're applying forces to 5 blocks, blah, blah, blah. In the diagram, is the coefficient of friction between the block smallest? So coefficient is going to be your frictional force divided by your normal force. And in theory, they're all going to have the same normal force because they're all 1 kilogram blocks. So then the question is, which one has the smallest frictional force? And if you're applying them at a constant speed, your applied force is equal to your frictional force. So this one right here, 2 newtons, has the smallest frictional force, so therefore the coefficient of friction should also be smallest. It's amazing how many of these we can do without even looking at the reference table. Okay. In the diagram below, shows a block sliding down an incline of angle theta. As the angle is decreased, the coefficient of friction between the bottom surface of the block and the surface of the incline will remain the same. The coefficient depends only on the 2 surfaces. The normal force would decrease, and thus the frictional force would also decrease, but the coefficient would remain the same, even though the frictional force is decreasing. Which pair of quantities could be used to determine the coefficient of friction for granite on concrete? Well, we know that the coefficient is friction force divided by normal force. So let's see, if you knew the mass, you could get the normal force. The speed, definitely not, so you don't need that. You do need the frictional force and the normal force. There we go. Coefficients of friction for 4 materials sliding over steel. A 10 kilogram block of each material's pulled horizontally at a constant velocity. So constant velocity means our applied force is going to be equal to the frictional force. Which block requires the smallest applied force? And the smallest applied force is going to be equal to the coefficient times the normal force. But 10 kilogram blocks are all 10 kilogram blocks, which means that they all have a weight of about 98 kilograms and thus a normal force of 98 kilograms. So the frictional force is just going to be the coefficient times 98. And so the one with the smallest coefficient is going to have the smallest amount of force. So that's going to be copper at 0.36. Here we go. The resultant of two forces. We've done this so many times. Hopefully you remember how to do this. Should look like this. 12 and 5. Boom. The resultant is going to be a triangle with a hypotenuse of something that's going to have to be bigger than 12 and 5. So you know it's not 12 and 5. And it should be the square root of 12 squared plus 5 squared. There's only one choice there. It's got to be answer D, 13 newtons. You can do the math to prove it to yourself. I think we're actually getting a little closer to the end here. A force vector is resolved into two perpendicular components, which represents the original force vector. So we add the components together to get your resultant, R. R should be down to the rule left. Answer D. Okay, two concurrent forces. So we see a lot of these vector things coming into play with forces, and then it's not just forces, but it's important to keep in mind we still do pay attention to vectors. Two forces have a maximum resultant of 45 and a minimum resultant of 5 newtons. What's the magnitude of each of these forces? Well, if the max tells you that, you know, A plus B is going to equal 45, basically saying when you add them together in the same direction, you're going to get 45. Whoops. A plus B is equal to 45. But if they're in opposite directions, A minus B is equal to 5. That gives you an answer of 20 and 25. Add them together, the max is 45. Taken in separate directions, you go 25 east and 20 west, for example, you're still going to end up 5 away. That's the minimum resultant. A 5 Newton force is east, a 5 Newton force is north. Concurrently means they act at the same point, so the resultant would be 5 and 5. So it's got to be a triangle that has sides 5 and 5 with a hypotenuse that is the square root of 25 plus 25. So it would be the square root of 50, which is about 7 newtons. Definitely can't be 10. We can figure that out. So it's got to be 7 newtons, and it is going to be going northeast. So 7 newtons northeast. Equilibrant would be 7 newtons southwest. That would be D. That would restore equilibrium. Okay. Which represents the forces acting on the block? Here we go. Weight goes straight down. So some of them, like B and C, definitely can't be true because they don't have a weight that goes straight down. The normal force has to go perpendicular to the block like that. And the frictional force is probably going to be going up this way, presuming the block doesn't have an applied force up the thing. So that would be answer D. There we go. In the diagram below, a box is at rest on an inclined plane. Which vector represents the direction of the normal force? It's going to be C. Boom. Okay. What's the magnitude of the force F if it establishes equilibrium? Oh my gosh, I'm going to guess that it is going at a, well, it's going to be balanced. I didn't even read this. You notice that? Don't need to. Because F is going to equal some component of this horizontal thing, and that component is going to be 100 times the adjacent side. It's this side of that triangle right there, and that side is 100 cosine 30. And so F is going to equal 100 cosine 30. Cosine 30 should be 0.866. So it should be about 86.6 newtons. In the diagram below, F is applied to the horizontal handle of a lawnmower, inclined at angle theta. Okay, the magnitude of the horizontal component of the force. So we just care about a force vector that looks like this. Horizontal is going to be that side of it, and that's a 30-degree angle. So that is going to be F times the cosine of 30. And So the horizontal component depends on the magnitude of the force F only. Nope. Not the angle only. Both the magnitude of the force and the measure of the angle. Yes. C. Okay. What is a vector quantity? Oh my gosh. Do we still have to know this stuff? Oh, of course we do. What is a vector quantity? Force. There we go. 58 through 60. We kind of, well, we did this in one of my classes. You might have done this already. 10 kilogram block sliding to the right. Acceleration is, find the net force. Net force is ma. Mass is 2 kilograms times acceleration of -2 meters per second squared. Sorry, 10 kilograms equals -20 newtons. The magnitude, which ignores the negative, is just 20 newtons. Notice I put an equation. Substitution with units. Unfortunately, not as neat as you probably should. Draw a vector representing. It should be, let's see, sliding to the right, so the force is to the left. Should look like this. I don't have a ruler, but this whole thing should be exactly 4 centimeters long. If 1 centimeter equals 5 newtons, so that means 4 centimeters equals 20 newtons. Calculate the coefficient of kinetic friction. So coefficient is going to equal your frictional force divided by your normal force, which in this case is going to be, your net force was 20, but that is caused by friction, so 20 newtons. Your normal force is going to be equal and opposite to the weight of the object, 10 kilograms times 9.8 meters per second squared. So that is going to be about 0.2. No units for that. Okay. Equation, substitution with units, answer with the correct units, which in this case is none. The Earth. This was a bit tricky. I'm going to encourage you to look at the reference table to get the right units here. F sub g equals g m1 m2 over r squared. So I need to pause this because I don't have a reference table in front of me. Okay, here's a reference table. There's G with the correct units there. There is the mass of the Earth. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Mass of the Sun's not on here because we need to find it, but we have the distance between the Earth and the Sun, 1.5 times 10 to the 11th. So you should get 6.67 times 10 to the -11th. Not a lot of space to write here, I apologize. Newtons. Let me think about this. Kilograms. Meters squared per kilogram squared. Okay, there we go. Get the right units in there. Newtons meters squared per kilogram squared. M1 is going to be the mass of the Earth. Really don't have a lot of space. 5.2